All right, we need to talk about how to find the dimension of a vector space. So a couple theorems from the textbook. If you know that a vector space has a basis, v1 to bn, and then you have like a set of vectors in V, but that has more than n vectors, then those vectors have to be linearly dependent. Because a basis, these would all be linearly independent. So if you have more vectors in your space, then they're going to be dependent in some way. Additionally, if the vector space has a basis of n vectors, then every basis of V must have n vectors. That's going to help us define what a dimension is. So the dimension of a vector space, we're going to write it as dim V, is the number of vectors in a basis for V. For example, standard basis of Rn has n vectors. Dimension would be n. If we're looking at, we call this standard polynomial basis, we call that P2. Notice that that has 3 independent vectors because there is no way to multiply a constant times 1 to get t squared. Same thing with t, so those are 3 independent pieces. So the dimension of P2 has to be 3. In general, any polynomial of degree n, the dimension is going to be n plus 1 because you have that constant term, okay, in there. However, the space of all polynomials, we can't count that, okay? But if you know the degree of the polynomial, then you can find the dimension of the standard polynomial basis for that degree. All right, let's look at another set of examples here. If you know that H is the span of 2 vectors in R3, so you can see here we have 3, 6, 2. Now that's this, I guess I was thinking in my head because 3 times 2 is 6. Nope, that's gonna be it. I mean, I guess you could divide everything by 2, but just leave it as 3, 6, 2. And then we also have 1, 0, 1. Notice 1, 0, 1 is in the plane down here always. Okay, and then this is going to end up being in here. And so that span is the plane between them. Okay. Therefore, a basis for H has to be those 2. They're linearly independent. Okay, and so we say that the dimension of H is then 2. Example 3, find the dimension of the subspace, and here is our H right here. So in this example, we need to see if we have linearly independent vectors. Let's break H into A times 1, 5, 0, 0, plus B times negative 3, 0, 1, 0, plus C times 6, 0, negative 2, 0, and D is 0, 4, negative 1, 0. So we can say then that H is spanned by these 4 vectors. But are they linearly independent vectors, right? We need to figure out what the basis is. Let's look at vector 1 and 2. Yeah, no way, because I have zeros in that spot. Let's look at vector 2 and vector 3. Uh-oh. If you look at vector 2 and vector 3, vector 3 is a multiple of vector 2. So we check that, that's okay. And then there's no way for us to get here. Therefore, the basis, right, this one would no longer be counted in our basis. And so our dimension of H must be 3. There's a couple other theorems here from the book just about dimensions overall. If H is a subspace inside a finite dimensional vector space, then any linearly independent set in H can be expanded to a basis. Okay, that makes total sense, and the dimension of H must be less than or equal to the dimension of V. We just kind of did a problem like that. Let V be a p-dimensional vector space where p is bigger than or equal to 1. Any linear independent set of exactly p elements in V has to be a basis for V. So that makes sense as well. It's kind of a extension of this right here. Like if you find a linearly independent set of vectors in V and the dimension of V is P, and you find P independent sets, then that has to be a basis because the basis can't have a dimension bigger than the vector space, right, itself.